Hello, everyone. This is Spencer Snolling from Hatch, and I'm glad that you could make it today to attend our regular GPSX monthly webinar. So I'm glad to be here with you. And today we're going to talk about what I guess I would call maybe one of the more advanced features that's available in GPSX, which is the ability to customize your GPSX model, to add your own code and your own calculations to a GPSX layout and build that all into the model when you run it, and then have it interact with the model in a sort of very open source kind of way. So it can be used for a wide number of things, as you'll see shortly, but I'm going to focus today on sticking to talking about flow control, because it kind of tends to be a good example, but certainly there's a lot of other things that you could use it for as well. So as usual with our webinars, I'd like to encourage everybody to type your questions into the Q&A panel that you should be able to access in Teams here across the top of your Teams window. So feel free to, at any point along the way, type your questions in there if you have any, and then I'll hang around at the end of the webinar and answer as many of those as I can. Okay, so the plan for today is I'm just going to talk about different ways to customize GPSX. So for a mature product like what we have and the way that we've developed it, where we want people to be able to get in there and do their own customizations, there's lots and lots of options. In fact, 4 more that I could cover in one particular webinar. So I'm going to stick to talking about using the Axle language that we have available, and I'll stick to a couple of specific types of scenarios, but we'll touch on some of the other options that are available as well. So we're going to use some examples where we're going to control some model parameters. With code, with a calculation, rather than having something come off of one of the menus. And I'll show you how you can customize your GPSX layout with new variables that you are going to calculate. And then I think the bulk of what we're going to do today is to go through 3 examples. This is very much a learn by seeing it being done kind of thing. So I thought I would do 3 full desktop examples today, doing things in different ways. These are kind of typical applications that we find ourselves doing on a regular basis. And then I have a few thoughts at the end about sort of good practice when you're doing this type of customization. And as I mentioned, happy to answer any questions that you have. Okay. So, as I mentioned, GPSX has a large number of ways that you can customize your models. And by customize, I mean really dig into and interact with and potentially edit and change the equations that we use in our underlying model, libraries in GPSX. So now, one of those, probably the one that's sort of most fixed and rigid, is to use our model developer tool. It is there for one specific type of customization, and that is to edit the matrix of biological reactions that we have in our models. So now it is there if you want to be able to get into the details of how fast the hydrolysis happens and what happens in inhibition terms on the biomass growth and so on. It's a very specific thing. Now we did do an entire webinar on this many years ago, which is still available on our YouTube channel. And if you're interested in doing that kind of customization, I suggest you pop over and watch that. So the second level, and probably much more flexible and open level and more detailed, is to integrate GPSX with Python. Now, with the most recent version of GPSX, we've now have this full Python integration where you can use Python to run the model. You can pass it. You can pass values to GPSX. You can set parameters. You can get data back. You can use all of the kind of power of the libraries and packages that are available in Python, and then have that directly interact with GPSX. Now, we've done several webinars on that. I recommend these here. This is the one from last year on just the very basics, how to connect GPSX and Python. Myself and my colleague Jacob Barkley went through the details of how to do that. And this is also a good one too, probabilistic design using Monte Carlo. This was from last fall. In there, there's several different examples of different things you can do. And Jacob, again, was there to show how you could do a bit of customization where we're setting the parameter values via equations and probabilistic calculations. And that was all done with Python as well. However, the oldest and sort of most useful and I think the most sort of easiest barrier to entry, lowest barrier to entry, the easiest thing to use is the customization features using the Axle language. That is the language which we have written GPSX, all of the wastewater content in. And it is relatively straightforward. You can access these files here. And I'm going to go through that and show you how that all works. You can right click on an open spot in your layout and access these menu items here. Go to the macros section. It'll open up a little window like this, and you can enter in equations here that will get automatically compiled into the model as it goes through the building process when you move over to simulation mode. So GPSX was designed with an open architecture. It is designed to allow users to develop their own materials, to add their own input parameters, develop their own new outputs, and the ability to interact with numbers that are being calculated that's there. So the idea is that we want you to be able to pick up the variables that the model already has and use those in your calculations to create new things. And the way that our menus work allows you to add create your own menus and add new variables to them. And then once they're there, you can then plot them on graphs. You can put your new parameters up on a slider. You can actually do a sensitivity analysis on your newly created input parameter or an optimization, for example. So these are all actually quite powerful features that kind of really set GPSX apart from some of our competitors' products. Okay, so basically, you're going to be editing those files as I was showing you earlier, and you can create as many new variables as you like, both for input parameters or, as I'm showing here in this output menu, you can write out exactly what you want the wording to say, and it'll appear automatically in this new menu as you have created it. Once it's there, by the way, you can take advantage of all of the regular functionality of GPSX. You can define something in one unit, but then use it in different other units, for example. So the typical applications of this are to be able to sort of automate the process of doing calculations with the information that comes into and out of GPSX. So, for example, I'm going to show you an example a little bit later here where you can change the plant loading. We can change flows and concentrations. We could calculate them from something. I know we can already do that by reading them from a file and other things too, but this is also sort of an algorithmic approach. One thing that we find, though, is probably the most significant use is to do control, right? So you could make your own different types of control algorithms by writing out, a bit of code to be able to say when the DO set point is this and the DO is actually some other number, I want you to change the airflow to something else. You can do if then else kind of constructs and so on, and all of that's there. And do it for aeration, pumping, chemical dosing, anything that you can set with a parameter in GPSX can be done that way. So here I'm giving some examples. Flow splitting is another one. I remember one of the most interesting ones that I did right at the beginning of my career was this very complex sets of parallel SBRs that kind of did things, and we wrote some code to kind of say, okay, if this one's full, then send the flow over there, but if that one's full, then you store it back, and we wait and we cycle around and so on. It worked very well, primarily because we have this very powerful flexibility to do this kind of thing. Right, and so that's for controlling inputs, but here you can also create new output variables, as I was showing you on that earlier slide. You can create, custom calculations. I saw recently some clients had some custom removal rates where there was a bunch of units on the board that represented a certain type of process, and they basically had flow in and BOD going in and BOD going out, and then they had a calculation that basically calculated what was the percent removal across those 3 units. That's not something that's already built into GPSX because it was particular to their drawing layout on their drawing board. But you can do that kind of a thing. Also, it's really good, for combining the output from multiple objects together, for example. But I also threw down on this slide here, anything else, like literally anything that you can think of, any calculation that you can think of. I'd like to multiply these 3 numbers together, or I wanted to take an average of a bunch of stuff, or calculate a moving average or something. You can do all of those sorts of things. Anything you can write code for can be done. So all of that coding is done in actual ACSL, Advanced Continuous Simulation Language. It's basically a language that we are using that is sort of a nice, convenient way to write out a algorithm and interact with the variables that we have. It is ultimately, after you are going through the build step, it is actually converted to Fortran. So ultimately what you're doing is you're writing Fortran. Any Fortran that you write will also work fine in this step too. So it's very similar to writing something in Python or MATLAB, or the if then else statements inside Excel. Actually, I find it actually easier to work with than writing out those long sets of brackets in Excel. But nonetheless, it's any other sort of math-based language. So, and also one of the really key things here is that GPSX actually allows you to control sort of when and how your new equations interact with the model. So you can have something that just sets something once at the beginning of the run, or maybe it does a bunch of trailing calculations when you get to the end of the run, or you can have it interact with it while the simulation is running. So to understand how to get in there and start writing your own code, one thing I wanted to review, if you haven't already noticed this, is that GPSX, when you save a layout, when you put stuff on the drawing board and you save it as your GPSX layout, it actually creates about 8 or 9 files. And these all together make up the GPSX layout. And you can use the archive command to zip them all together if you want to send us a text support question, for example. So I just took this screenshot really quickly yesterday while I was setting up a few things for today's webinar. And you can see here that there are a number of files. They all have the same layout name at the beginning. That's the name that you choose. And then they have a bunch of different extensions. And it's in these files where you will write the code that you want to be able to do and do the customization. So the ones that end in .usr, that is the custom equations and algorithms. There's different sections within that file to do things at certain times. And the con is for constants and var is for output variables. So those are files. They follow a very specific type of syntax for being able to use them. And basically, I'll go through how that works. And we have lots of details in our user guide. But basically, you're going to write out a line for every variable that you have. And then when you load your GPSX layout, we parse that file and create the new custom menu for you that you have created. So just to give you a quick highlight there, this is the one, the user file that for the custom calculations, and then the output variables are there as well. Oh, I'm actually pointing to the wrong file. This should say con here. Put the box around the wrong thing. Sorry about that. It's the con file that is the one that you have. Now, these are all regular ASCII text files, right? They're just you can edit them with any sort of flat text editor of any kind. Now you can do it either by clicking on these menus like I'm showing here in GPSX, and we'll open up a little internal editor for you to play with, or you can do it outside of GPSX. I tend to do it outside, mostly because I happen to like Notepad++ as a text editor, and you can use it for that as well. So when you are going to do the customization, you can go here. I'm going to show you, I'm going to stick to doing it inside GPSX for the rest of this afternoon's webinar. You can go here to the user files menu. So what you do is you find an open space on your drawing board somewhere with just a white background, not on an object, and you right click there, and then you can access these menus. Go to user files. This is the place where you will edit the content of these files. And when you come back later and look in the user section, that's where the new menus that you're creating will show up. So the macros is the section where the algorithm and the calculations go, and there are different sections here, and I'll cover that shortly, how to decide which part to put it in. And when you go to the constant section, this is editing the .con file, and you can see here that there's a certain syntax that you'll be following. There's nothing here yet, but we're going to add something to it. This is where you can specify the details that will go on the input menus, and then we have the same thing for the output menus. Now, all of this functionality is already covered very nicely in Chapter 11 of the GPSX User's Guide. If you go to the Help menu and go to Manuals and go to User's Guide, find Chapter 11, and it talks about all of this. It does include A lot about the syntax that you'll need to be able to follow. It's a good reference guide. And so quite coincidentally, if you go to our tutorial guide, tutorial 11, same number, is actually the tutorial where we go through doing some of the kinds of things that I'm going to be doing today. And you can also go to our YouTube channel and watch the tutorial being done there as well. So now I've chosen to do a couple of different examples than what we're doing in the tutorials today. So one of the funny side effects is we've actually changed tutorial 11 several times over my career. Every time we come up with what is a really good idea for like a customization, oh, we can make an on-off controller or whatever. we ultimately end up deciding, hey, we should just make that an object in GPSX, and then we have to go figure out something else for the customization tutorial. So we keep coming up with good ideas and then actually implementing them as a standard part of GPSX. Right. Okay. So the way you go about doing it is you're going to set up any input parameters that you want in the conf file, one line for each, and there's the syntax that you will follow. Any code calculations that you want to do, so you can use those constants that you've set up in the conf file as your input, or you can use any other model variables, like say you want to have the influent flow or the mixed liquor concentration, or the wastage mass flow or something like that. Any of those things can be picked up. You can then do calculations of any arbitrary complexity and then set parameters in the model. You can overwrite what is going to be appearing on the menus by just setting that using these calculations. And you can create new output. You can create new variables, and those can then go on to their own special new menu in the var file. Now, once you've done all of that, you need to reload your GPSX layout and then also go through the process of rebuilding it. Now, most of the time, GPSX will detect that something has changed, and you can go straight over to simulation mode, and it will detect that and automatically ask you to rebuild it. However, if it's possible, if you were using an outside editor, it may not have noticed right away. You can just go to the tools menu and trigger a rebuild from there. Now, in this user file where you're going to be putting your calculations, the different sections in the user file are executed at different times in the simulation. And this is actually a very handy type of tool. So say, for example, I may want to do a bunch of calculations at the end of the simulation. I don't need to do them every time step. And so therefore, I'll put them in the terminal section, and they'll only happen once at the end. So you can either initialize things ahead of the simulation or do things at specific intervals. And there's quite a lot of functionality and useful functionality in this area. So just to review what all of these parts mean. Now, if you open up the user file, either in GPSX or in your notepad, you can find that if I put calculations here in what they call the initial section, this is basically done once at the very beginning of the simulation and never done again. So this is where you can sort of initialize a number of things or do a bunch of calculations up front that really only need to be done once. The derivative section is where calculations are done at every time step along the way. Now, anything to do with control probably needs to be done here. This is basically, I want the model to always be doing this calculation all the time. Now, there is another section here, which is also happening during the simulation, but this is now done less frequently. This is done every communications interval. So communication interval is how frequently we update the model. So you may think that we actually update our graphs every time the model takes a step forward and produces some new numbers, but that's actually not the case. In GPSX, as the simulation is moving forward in time, it's taking a very small time step. Like usually it's like maybe 10 or 15 simulated seconds at a time as it moves forward. Now it goes really fast, of course, because we've got a good set of solvers that we work with. And then we have a setting. It's actually in the same menu where you find the stop time. If you look to the communication interval, we have it set to, by default, 0.05 days. So, which is every, I think, hour, just over an hour, right? So every hour, what it's going to do is the model then, our interface then checks in with the model, gets a bunch of values, plots them on the graph, and then lets it sort of take its steps in the background, and then checks in next hour, updates the graphs, and so on. Now that all that happens so fast, it's not too worrisome, but it does keep down the number of calculations that we have to do, which is how we keep GPSX running smoothly. Now in here, these calculations are going to happen only every communication interval, or you can actually write a section here that where you control the amount of frequency of that communication. Now, I almost went into making a huge demonstration of this for today's webinar, and then I realized that the webinar was going to be way too long if I did that. So maybe we'll do a follow-up version of this webinar at some point next year, and then I can get into those details here. But I'll just let you know, if you want a discrete event to happen, you know, every certain time period, and or you want it to happen at a very specific time in the simulation, you can actually do some coding here, and I can give you a hand with that. And then lastly, of course, these are the terminal section. It runs once at the end of the simulation, so you can kind of do some follow-up calculations. You know, you might want to, you know, do one of those efficiency calculations. You know, what was the BOD removal percentage? You know, that kind of thing here. Right. Okay. Now, the important thing to know is that all the calculations are done using GPSX cryptic variable names. And by cryptic, we mean a short name that is calculated that is unique for every variable, and it is not the descriptive name that you're seeing on the menus. So you can find out what the short cryptic name is by holding your mouse over the variable in any GPSX menu. So I took a screenshot here. You can see that for the particular menu I have, this pumped flow rate. If I hold my cursor over it, a little tooltip will pop up and it shows the descriptive name on the left and then the short cryptic name on the right. The cryptic name is actually if you look into the actual compiled Fortran, that's the variable name that we're using there. So in this case, that pump flow is QCon3. Then you would use this variable in your actual calculations. Now, the good thing is, rather than relying on remembering what this thing is, you can actually right-click on any variable, and then you'll see here that you can either set up a data file, or more importantly, you can copy that cryptic name to the clipboard. That's the very easiest way to do it, is just copy that name to a clipboard, and then you can paste it into your code that you're writing. So for example, I can copy that, paste it here. I want to, with this equation, set the value of this pump flow rate here, and I'm going to make it equal to the stuff that's on the right-hand side of this equation here. So QCon3 is equal to a volume times a storage constant, and so on. Note here that if you put down an exclamation point, anything after that is ignored. This is the way you can comment your code very nicely. So we recommend doing that as well. Now, there's a lot of functionality that you can take advantage of, a lot of functions and pre-programmed abilities that are available, and you can we can send you a copy of the the Axel reference manual that has the names of all the various functions that you can use, and we're going to use one of those when we're generating some random numbers here in our second example. Okay, so time to get on with doing some interesting things. So I'm going to start the first of the three demonstrations here by just creating a new output variable, and then we're going to put it on a menu and plot it, and we'll see how it goes. So as per usual, I'm going to actually build this live as we go. So basically, I decided to, very first simple example is I want to calculate a new variable that is the wastage rate as a percentage of the influent flow. So basically, here's the influent flow. I want to capture that number there, and I want to capture this this wastage flow rate, and I'm going to divide that by the influent flow, and then set that up so that I can have it as a percentage, and then put that on a menu. Okay, so here's the GPSX layout. Now, I haven't done any customization yet. I just built this thing up as it stands like that. And so what I'm going to do is I am going to just run it once and show you what it looks like. So it's obviously a typical layout. I've used mostly the default settings for everything here in terms of their flow and size and whatnot. So if I run a steady state solution, we can see that we have a plant that is, if I double click here, we can see that, you know, TSS is 11. And the ammonia is less than 0.1, so, you know, fully nitrifying, BOD is low, everything's hunky-dory there. Okay, so what I want to do now is I'm just going to show you the flow across the entire plant here. And in case you've never tried this before, you can use this Sankey diagram here, additional output displays. This visualization button is what that's supposed to be. I'm going to use a Sankey diagram. That kind of shows us where all the flows go in and out of our system. And we can see here that the flow from this wastage point is 26 meters cubed per day, and the influent flow is 2,000 meters cubed per day. So we are going to expect a small a small percentage, a few percent. That totally makes sense. Your WAS flow should be, probably less than 5% of your influent flow under most circumstances. Okay, now since we're doing customization and we're going to have to ultimately rebuild our model, we're going to have to go back to modeling mode, first of all. And I'm going to open up that menu that I mentioned before. So I'm right-clicking in the background here. I'm going to user files. I'm going to open the macros menu here. Now I got this little window, and I'm going to open this up a little bit. And this is where I want to start typing in the various equations that we're going to use. Now, I need a couple of numbers here. So I'm going to move this over on this side so I'm not covering up the board. And I want to find the cryptic variable names of this flow and this flow because I need them for my calculation. So here's the wastage flow. If I go here and I right-click on that connection point and I go to output variables and flow, this is telling me here that this is the flow for this point. And what we can see is if I pop here and just hold that, you can see it's Q was. And as I mentioned, the much easier way to do it is actually copy that cryptic name. And I'm just going to paste it here. And we want to divide that by, actually, you know what? I should probably set up my actual new name first. The new variable that I'm going to be creating, I'm going to call was fraction. There we go. Was fraction equals that Q was variable that I had before. And then we're going to divide that by the influent flow. So I can get rid of this and this influent flow right here. So right click, output variables, flow, and we're going to want this one. And I'm going to copy that cryptic name and it's QWWinf, right? Okay. So that's going to give me that fraction. Now, the original slide there, I said I wanted to do this actually so that it was a percentage, which means I should take this whole thing and multiply by 100. So let's do that. And times 100. Okay, so that is an example of just doing and creating a brand new variable here, and then doing the calculation that I want to do. And one thing I also really recommend doing is at the end of your calculations is put an exclamation point and actually say what this is, because it's easy to remember if you do a calculation and then forget later on. Coming back, you'll thank your past self. Your future self will thank you if you do this. Basically, making notes here as you go along. Okay, so I'm going to accept that. Now I also want to take that variable that I had, which was called was fraction, and I want to add it to our custom menus so that I can then plot it on something. So again, user files. In this case, we're going to output variables, and we are going to add this kind of comments here that tell us exactly what variables we want to create. Now, you can see here it says menu item and header, just so that you know what those are. If I open up one of these menus here, I'm just going to open up one of these things. If you see here, for example, output variables, these are menu items. There's 5 different menu items that are available here. So you can actually create multiple menu items in this menu here, and you'll see different menus get sorted out and pop up here. And once I do open one of those, you can see here that we group variables into bunches here. So you can see solids variables. There's a line drawn around a certain number of parameters. This is what the header is, right? So you can make a header here and do that. So I am going to create a new one here. So I'm going to say this is my new was fraction variable. All right, then the way that you create this now is you type display, and I'll type was fraction. I'm just going to double check if I go back to my macros here that I'm actually got the right cryptic name there. Was fraction. I only typed that 2 minutes ago, but I forgot what I typed. Okay, there we go. Was fraction. So we're going to that display means it is now going to be available for you to plot in the future. So was fraction, and then now I can describe what this is. So we'll say was flow as a fraction, oops, of infinite. And then we know that we did this in the, you have to put the units here, and we know that we did this as a percentage. Percent. All right. And we accept that. Now we get a message here, you must reload the layout for changes to take effect. That is because we need to parse this. So the easiest way to do that is actually go to File and just select your name again. Save that and it will reload. It takes a fraction of a second. And now the key thing is to go to this user file. Now, these are where our new input parameters. We haven't made any input parameters or initial conditions, but we did make our new user-defined output menu, and there it is, right? My new was fraction variable. Here it is, the percentage, and so on. So that's all done. Very good. And now we are ready to rebuild the model. So what we should see is if we move forward here, GPSX knows we need to recompile the model, which is now doing it again. So it's going through the process of collecting up all of the data that's on all the menus and all of our equations in the background for doing activated sludge and everything else, along with this one new parameter or one new equation that I just added. And after a few seconds, we should be done and ready to go. So what we can do is I'm just going to run a steady state solution first. So let's go look at that menu, user, output variables, user defined, and we can see here, there's my number, 1.3%. And so, but now this is a fully functioning GPSX output variable. We can, generate a report. We can plot it on a graph, which is exactly what I want to do here. I'm going to plot, I'm just going to drag this over here. And now we've got this output menu. Now I'm going to change the scale since we only want this to be, since it's percent only from 0 to 100. Now, the thing is, it's a very small number, so we probably really only need like 10%, right? So, and let's run a few days of simulation here, and then we should see our new value being calculated. If I change the influent flow, the fraction, of course, changes because we're recalculating it every time step. So this is kind of a very simple example that I don't know if you would find that to be useful for your calculations, but just to give you the feeling of how you could do this kind of thing. Do a calculation of whatever kind of thing you want, pick up the variables that you need from the menus, put them in your equation, and then now this is a new calculation that's happening all the time. Okay, now let's go on to something a little bit more challenging and interesting. So let me see here. I see we've got a question here. So as you're going along, as I'm moving along here, please feel free to type your questions in the Q&A window or the chat window. Either one is fine. Okay, so the next thing I want to do is actually make a little bit of a random event happening, right? So by default, GPSX is a pretty deterministic kind of thing. We don't implement any randomness unless you specifically want us to. So, so adding a bit of a random thing is kind of an interesting technique to do sensitivity analysis on your model. And so what we want to do is actually generate a random batch delivery of food waste into this wastewater treatment plant. So here we're going to have essentially the same plant that I just showed you, but now I added in a truck. If you're not familiar with the truck influent, it represents a batch delivery. You set it up just like the same way that you would set up your regular influent. However, it has a bunch of different parameter settings. It allows you to say that a certain number of deliveries will happen. Typically this is set up to do septage deliveries, but I'm setting this up as a very high strength food waste. And you do that by opening up the flow menu here. You can either set it as a constant like you would normally, or in this case, a number of individual truckloads. So if I click on this button, that's going to say here that you specify, if you have multiple trucks, you could specify different values for each of these, but I'm just doing one delivery per day. A certain volume is going to be added, and it's going to happen at a certain time, and it's going to end at a certain time. So what I wanted to do was to run simulations where we can do some random number generation of these values so that you can have a little bit of variability of things going on in your layout. And we're going to use one of the pre-defined Axel functions called unif, as in short for uniform, where we're going to generate a random number of uniform distribution between a low value and a high value. And by that, I mean is, you're equally likely to get any value in that range. It's not normally distributed, it is uniformly distributed. So what we're going to do is we're going to specify that we get a certain load coming into the plant between two different values. We're going to specify that the flow coming into the plant will start at a certain time. I'm going to do it so that it kind of is in the morning. And then we'll have a ending. Now, this one is a little bit extra complicated because we don't want this thing to happen before that. So what I'm going to do is I'm going to take this time and then I'm going to add some small number to it of a duration, and then that will tell us exactly when it's going to end. So these are typical uses of doing some customization, and we're going to do some something interesting there. Okay, so now I'm going to move over to demo number 2 layout. Right. Okay, so now here I'm going to open that up. And I just want to basically show that we have the truck here. I actually set up the influent characterization to be quite concentrated. I wanted to do that mostly just so that you can clearly see what's happening in the layout, but you can see here a very high concentration of 25,000 milligrams per liter of incoming COD. And as we mentioned here, if I go to the flow data menu for the truck, I've got it set to individual, and here's our numbers. I've set this to 0 at the moment because I want the thing to start out, and then we're without any trucks happening, and then we're going to bring in some custom calculations to control that. Right, okay, so I'm going to run it once just to show you the output before we start doing the randomness stuff. So this is more or less, as I said, the same layout as before. So we're getting, roughly the same kind of performance. Now, I'm going to show you a one-day dynamic simulation here, and you can see that the effluent TSS, if I click here, it's 11. It's more or less the same output as we had before. Now, I'm going to do a dynamic simulation because we want to see how things start and end. I decided to leave out the daily diurnal pattern here just because it's a little easier to point out exactly what's happening. So that's why these are completely flat lines at the moment. Right. Okay, so we got to go back to modeling mode because we're going to be adding some equations. And again, we need to find those cryptic variable names to be able to do what we want to do. So in this case, we are going to open up our macros. This is where we're going to write some new code here. And in this case, we're going to put it in the initial section. That means we're going to generate a random starting time for the truck and the random load and the random duration all up here in the initial section. And we're only going to run the one-day dynamics, but just so that you're aware, if we were running multiple days, it would repeat the same thing every day. That's kind of the way our truck object works. We would have to go into a little bit more details if we wanted to have a random truck with different arrival times each day. That is also possible, but I stuck to the simpler example for the moment. Right, okay, so in this case, we need, first of all, to set some of these variables here. So I'm just going to move this out of the way, and I'm going to be grabbing these variables so that I can paste them in. So we want this one, first of all. So I'll do that. It is Q load, and then food is the variable there. And I'm going to use that functionality that I mentioned before. I think I have it on the slide here. No, I do not have it on the slide. Okay, so the way, oh yeah, I did have it on the slide. Yeah, sorry. The way it works is you type in unif, and then you put a low value, comma, a high value, and then close the bracket. So in this particular case, I'm going to set it so that our load is anything between 0 0.0 and 20 meters cubed. So that would be quite a big truck, but nonetheless, we're going to say here's all the range of possible loadings that we could get. Okay, next one, we got to do the same kind of value that we're going to set for the starting point. So I'm going to grab that cryptic variable, and we're going to do the same thing, unif, and we're going to say I want to start, let's say no earlier than 5 a.m. This is in hours, by the way. And we're going to go all the way to potentially starting at 8 p.m. All right, so that's that. And then the last one, let's grab that cryptic name and run this. And so that's the last one, unif, and then in this case, we're going to say we want the duration. Oh, no, sorry. One thing I needed to do is I want to have the ending time to be equal to the starting time plus a bit of duration here. So I'm going to copy this name here. It's this thing plus, and then unif. And then I would say anything between half an hour and 3 hours. That sort of seems like, I don't know, I'm randomly picking some lengths of time, but it'll do the job for explaining things. Now, that is sort of everything nicely set up. By the way, I didn't go all the way to 0 here because the way this works is we take this volume and then we basically put it into this period of time. So if we actually ended up with a 0, or close to 0 duration, that would actually mean an infinite influent flow rate. So that's why I'm making it no lower than 0.5. Okay, so that's all good. So let's close all this out, and then I'm going to save it. Then I'm going to rebuild it. Move over here. It's going to pop up the compiler again. And then we can plot that. So basically, I set up the flow rate from the food truck here. And that is going to be basically a square wave, and it will be located at a different point in time and a different intensity and different duration based on those numbers that we had. And what we can then do is we can see what is the effect on the the effluent from the plant. Okay, so randomly generated truck arrived here. Let's switch this scale here to hours. And we can see here it arrived just after lunch, dumped off that flow for just a very short period of time. And if I run it again, we get a different duration, much less load, but for a much longer period of time. And then we can just run this over and over again. And so you can see how it can generate a number of different interesting results. Now, this would be really handy. And in fact, we used almost this exact example in the webinar that I mentioned about probabilistic plant design, where we had randomly generated truck arrivals, and we ran a large Monte Carlo simulation. If you've been to our webinars before, you know that I'm a fan of using Monte Carlo in certain situations, and so that's kind of was the genesis of this concept here. Okay, so we can see that every time I run it, we get a different truck schedule, and we can see that the effluent quality is affected by that. Now, it's not a very big delivery, so you can see that sometimes the bumps are a little bit less or more. See, this one was much smaller than the previous one. I bet you it's because, yeah, it's not a very long delivery and the magnitude isn't that big. So let's run one more. Let's see if we get something more interesting. Yeah, not too bad. Anyway, I think you get the point. It's basically a new feature, a new type of control of the inputs to the model. Oh, this is next to nothing, this one. Oh yeah, that's a very small delivery. So now you could go back and actually make out multiple trucks and have them all doing their own separate thing. And, those random times when maybe 2 trucks come at the same time. Or one right after another or so on. Those are all kind of interesting things to do. You can also use this kind of approach if you wanted to have a, random weather type event, using these types of random equations to generate weather is also a very popular thing. Okay, all right, so that's that. And now let's move on to our most complicated example, the last one, where we're going to be using some control kind of approach, a control algorithm to set various parameters while the simulation is going. And we're going to do it in the context of having a wet weather event happen. So I just want to double check, make sure I didn't leave any code in here from when I was rehearsing this earlier. I did not, so we are good. And basically, in this case, I'm just going to show a quick slide here. In this case, there's two new parts to this model. So again, the plant is pretty much the same thing. But now, after the wastewater influent, we have this control splitter. The control splitter is a very handy splitter that's available to put on the drawing board that can do bypassing or, pushing flow over to an equalization tank or bypass. So in this case, I set this up such that we've set this feed to be set at 2,000 meters cubed per day, which is the default flow that I was using in all of the earlier examples this afternoon. And anytime the flow becomes bigger than that, we'll still keep the 2,000 going this way, and all the rest of the flow will come up into this equalization tank. So this is going to be a big, big storage tank, and I've set it up. It starts out empty, and then it fills up while the storm is happening. And then later in the run, when the flow is lower, we're going to try and pump it back. So here's the influent flow that I made up, and then this is done using a data input file. So we get exactly the same flow or pattern of flow every time we run this. So here's 10 days, and we can see that at the beginning, well, most of this flow is going to go over to the equalization tank or I&I tank, so to speak. And then after we kind of get back to normal flow, we can see here that it's a bit more normal, but it's still dynamic. This is the period in which case we want to pump back and empty out that storm tank. And you can see there's even periods where it's quite a bit less than the default. So maybe what I want to do is take advantage of that by doing a calculation to kind of ramp up the flow back, when there's that opportunity. When the loading is low, let's bring back even more from the equalization tank. So just to set the context, if I don't do anything, then I get this. This is basically terrible effluent quality. So as soon as you can see here that during this period of time, the equalization tank was doing its job, but then it kind of filled up. And then as this kind of kept going, we had huge overflows and so on. So we're going to try and improve upon this terrible situation. So just to remind you, basically, we've got this here controlling only 2,000 meters cubed per day goes through the system. All the rest is going to go up to the equalization tank. We have the ability to pump it back at whatever rate that we want back into the system while the 2,000 is still coming along. And then what we're going to do is we are going to write an equation as an approach here based on this number in order to be able to sort of specify how much we want to pump. And I tried different things, and just for the sake of simplicity, I kind of went with this. Basically, we want the amount of flow coming out from EQ pump to be equal to some threshold value that we're going to set minus this amount. So basically, we're going to say the difference between what's coming in and some threshold that we're willing to be able to play with. So this is a new parameter that we're going to be setting up and putting on a menu, and we can therefore play around with it a bit. Anytime, if we don't pump it back enough, the problem, you can see here that the overflow from the EQ tank basically goes straight out to the effluent. So that's why we were getting some huge numbers over here. And so I want to be able to avoid that. Okay, I realize that might not be the absolute most realistic thing that the way a plant would be organized, but I wanted to have something that I could do in 10 minutes for the demonstration today that kind of has a little bit of a realistic feel to it. Okay, so here's the plant itself. And so what I'm going to do is I'm going to start by running just the first part of the simulation where the big flow happens. So let's run a 3-day simulation, and you can see here I'm reading this in, right? And so if I go to the flow control, here's the flow. You can see this is being read from the file, and it goes up and it comes back down. And then I'll let it stop on day 3. We're going to run 10 days altogether here. So if I look at the equalization tank, this is a time series of the volume that is stored in the tank. So at the beginning, it was empty, nothing happened. The flow hit, it exceeded what we were allowing to go through the control splitter, and so it now filled up. So I made it big enough that it doesn't overflow, and we can see here that right now it's pretty much full. And so what we want to do is we got this much flow, we got to pump back again. So what I'm going to do is we are going to implement that equation and that new constant, that threshold, and then we are going to build that, and we're going to put the threshold on the slider, and we're going to play around with that as it goes. Right. Okay. So as you, I'm sure you can imagine, we right-click and we go to user files. In this case, we're going to go to constants first, and we're going to set up our threshold here. So I'm going to call this under this header here, wet weather control, and constant is how you start this, and you give it the name. We're going to call this threshold. And I'm going to set it to 0 for the moment so that at the beginning of the simulation, oops, sorry, I forgot the equals, threshold equals 0. At the beginning of the simulation, while the storm is happening, we don't want to be emptying it out. So we're going to leave that at 0. And then we're going to call this EQ pumping threshold. And this is in meters cubed per day. All right. So we're going to save that. And as it mentions, we need to reload the layout so it can reparse that and do its thing. Okay, if I go to users, input parameters, here's that new parameter that I just created, right? Okay, all good. Now I need to actually use that in the calculation of this pump rate here. So we'll go to macros. Now, just to make sure that you're clear here on the context, I am now putting in, and I'm actually setting the value, just like we were before, setting the value of this pump. And we're doing it in the derivative section, which means it's happening all the time. And so as the flow changes, as things are happening, it will redo this calculation. It will change this the pump rate here instantaneously all the time. So first of all, I need to grab that pump rate cryptic variable name, which is right here. Copy that, paste, and that out of the way. And then the rest of our equation that we did before was threshold minus this flow right here. So I'm going to grab that one, flow, copy that cryptic variable, Q feed, and then done. All right, so basically that's all that'll happen. Now this means that even though the EQ pump is a variable that is on a menu, it's going to be ignored. It's going to be set from the new calculation that you are doing here. Okay, let's go over and build it and run it, and hopefully it'll work out the way that I intended. And hey. Okay, so one thing we're going to need to do is we want to plot this. So I'm going to go plot flow rate. Put this on here as well. Okay, so now we're set. We're going to run the 3 days. Oh, wait a minute. Before we do that, I forgot that I want to have our new parameter up here as a slider. That's the other thing. There we go. Okay, so now this variable is something that's probably going to range between 0, like I think we're going to try to get this up above. We want to have it above the default value of 2000 flow so that we can actually drain the tank. We want to have more flow coming out. So let's put like 5000 here. Okay, so we're going to do the 3-day simulation to get that started. We can see our tank filling up. Right. Okay, so now we're going to go to 10 days, and I'm going to set this to 2500. And we're going to continue. Okay. Oh, I've got a scale issue here. Just let me make this equal to the scale of all the other ones. There we go. So what we can see here is that the flow is when I turned it on, when basically we set this EQ pumping threshold, it is now saying that these things are coming along. And what we're doing is we're plotting this value that is the pump rate. So you can see here that when the flow drops like when it's high, it's still trying to pump down the equalization tank. But when the flow drops below that 2000 value, the fact when this drops below its sort of limited value, that this provides us with like an extra bit of volume, in which case we can take advantage of, right? So we can see here that that allows us to then sort of pump down the volume of the equalization tank. So over 10 days, we got it down, what, to maybe a third roughly of where it was going to go before. So we can see here that that's not too bad. Now we can optimize this by trying a different value. Oh, before we do that, let's take a look at how the effect on the effluent concentration, right? Well, you remember before it was a big disaster. Here you can see now, of course, we have everything under control. We're pumping it back at a rate that is acceptable and can be handled by the activated sludge system. So you can see here, obviously at that point when we start pumping it back, it does have an effect. The TSS goes from 11 up to 15. So, that's not too bad. It's still sort of doable, right? But we did only get it down this much. So if we wanted to do it faster, that means we need to have a higher threshold, a higher value that we're going to work with. So this bring this line up a bit, right? So let's do 3,500, and I'm going to run that again. Now I'm going to have to reset the whole thing here. Let's put this back to 0. I want to reset the whole thing because I got to fill up the tank first. So we're going to do that same exact sample over again. We're going to let the big wet weather event happen. We're just storing everything. We're not bringing anything back. This pump is 0 at the moment, as you can see along the bottom here. Okay, so then we go to the equalization tank. We can see it is full. Now let's do this at 3,500 instead of 2,500, and let's see where that gets us to. So there's 10. I'm going to continue on, and so this is now higher than it was before, right? So if I look at the equalization tank, it's now being pumped back, so faster. That's a sharper decrease here. So. Right, so you can see here that this is now doing a better job. It's still taking advantage of those things, but you can see here now, it basically goes to 0. And why is that? Well, basically, we pumped it all back. So now there's nothing left to pump back from the tank. It's back to being empty. And here's a little period where actually it went up again, and we're pumping it out immediately. So there you go. Now, what was the effect on the effluent quality? Well, a much bigger effect, right? We're pumping more flow, through here. So we can see the TSS, instead of being at 15, is now over 20. So this is the cool thing, right? This is the part that you can use this kind of a tool to investigate and optimize this situation, right? You can take your parameter that you created and put it on the GPSX optimizer and let it figure out, you'd have to define exactly what the most meaningful optimization would be, but you could make that a function of these things that are happening here. So it's all really, really cool and interesting stuff. And like literally it is sort of open-ended. You can do whatever you like. So here's a few other examples. I realize I'm going a little bit long, if you can hang with me. You can combine different signals. This actually came up in a project that we were doing last year, where we were modeling a fairly complicated aeration control system. And as one part of that, they actually had multiple DO probes and took the average of those. So that's an example where you would use customization to create a new signal from a bunch of signals together, and then put the controller on that. So you can create other types of intelligent automation, algorithms like the one I just showed you to adjust flow rates and dosages and so on. New outputs, you can create new bar graphs, you can do whatever it is that was most useful to you. And that other thing that I mentioned that I didn't have time to get into today, which is creating discrete events that happen at a prescribed interval, once per shift, somebody comes in and makes a change to something, and you want to model that in your model, or, an actual event where every Thursday afternoon at 2:30 p.m. something happens, you get a delivery or whatever it is. And lastly, I know some people who've set up quite interesting alarms that just print stuff or just set flags or do things that in a way that is useful to that are a very specific set of conditions, and you can just use GPSX to alert you when those conditions are being met. Right. Okay. So last few slides, just a few things that I suggest you do while you're doing this, in addition to making sure you comment all your code. All calculations have to be done in the GPSX default units, which are SI metric units. So anytime that you come across a length or anything based on a length, that's going to be in meters. So volumes are in meters cubed, for example. Even if you're plotting it on a graph in, say, millions of gallons, the actual variable is being calculated in meters cubed. So just keep that in mind. Mass, anything based on mass is going to be in grams, and anything on time is based in days. So you can figure out what the combined unit of all of those things will be. And as I suggested, make sure you comment your code with an exclamation point at any point along the line, and then everything after that is ignored. So one thing just to keep in mind, one thing you should not do is have a variable both on a slider and being calculated in user code. If you end up with the same cryptic variable in both places, they basically fight with each other. It'll end up being set to the value on the slider some of the time and being calculated some other time. It'll flip back and forth based on communication interval. Anyway, it's a conflict. So if you're doing I'm assuming most of the time, if you're doing the calculation in the user code, you don't want to have it on a slider. You want it to be calculated. One thing to also keep in mind here, and this is of course true for any mathematical language, is to watch out for division by zero errors. So actually, in that very first example I did today, I divided by QWWinf here, and theoretically, if that number went to zero, I knew I wasn't going to set it to zero in the particular example I was doing, but if theoretically it would actually cause a division by zero error, and basically it will just cause the model to break all of its mass balances if you do that. So we have an actual useful little constant that is the protection against division by zero, also known as PADBIZ. So you can actually use that in your equations and basically just put it on the bottom half of your equation. Just add it to whatever is the bottom half of your equation. It's a tiny little value, 1 times 10 to the minus 10. It's there so that it doesn't change any value that you end up coming up with. Like all your calculation will be exactly the same because it's so small, but it is not zero. So it will prevent that problem. Also, if you're doing an integer in your calculation, please include the 0.0 on the end of the value. That is to actually protect against the very unlikely but slightly possible situation where the Fortran compiler wants to combine a real number with an integer, and it may do some rounding on you by making the answer an integer as well. So just if you do it like this, it will always avoid that problem, and all of our code is written that way. So if you make a mistake, if you actually have a typo or a syntax error or what have you, when you go to the building section, which you saw several times as I was doing things here, it will be shown here that you'll get this converting layout to code, and then it'll stop and it'll say Axel detected an error or warning. And here it is, symbol used but not defined. This particular situation is very common, where basically it found something on the right-hand side of an equation that was never defined on the left-hand side of the equation anywhere else. Excuse me. So basically, this is basically saying I don't know what this number is. Now, the Axel manual that you can use has descriptions of all of these typical errors and how to look for and find the solution to them. So, and you can always send us a tech support question, and we'll handle that out too. Okay, so a little bit longer than I intended today, but hopefully you found it useful. The final thoughts for today is that this customization feature is extremely useful for implementing your own equations, calculations, and control algorithms into the models that you have. Those things that you're typing, those cryptic variables, will be very specific to your own model. So if you change a label, you may have to change your equation. But they are there, and it's very easy to use, and really truly has like sort of unlimited applications as we went forward. So it is something that is really a powerful aspect, and I know a large number of our users really like to take advantage of it and find that it really does add value to the modeling effort that they provide to their clients. So what I'll say is, I'll wind it up with, if you have an idea of what you want to do, but you're not even really sure where to start, send us an email. We'll help you get started. We'll point out what kinds of calculations that you should do.